The first thing that we want to talk about with Le Chatelier's principle is we're looking at systems at equilibrium. Okay, so they are at equilibrium, and what we're going to do is we're going to impose a stress on the system. In other words, we might change the temperature, we might change the volume, we might remove some of the material that's actually within the system itself. So I'm going to go through the three on here. The other sheets that I gave you were supplementals to help you understand this, plus the video is going to be nice. I have a video, not a video, but an animation I'm going to show you. That'll help as well. So there's a lot of things to help you with that. So go ahead and put this sheet, the single-sided one, off to the side just for a moment until we talk about temperature. All right, so the very first statement, or the first statement at the top of the page there says, Le Chatelier's principle states that a change or a stress is imposed on a system at equilibrium. And that's really important because the system is at equilibrium. It's not going to equilibrium. It's at equilibrium. And then we're going to change something about it. Okay? What? Yeah. All right. The first one that I want to talk about is concentrations. So when we talk about concentrations, I'll put a generic equation up here where we have A plus B, and it generates C. Actually, I'll use that for quite a bit of things. The system's at equilibrium, and we have our K, where it's C over A and B. Actually, let's put a 2 on that, just to make it more fun. Okay? So there's our equilibrium expression, and whatever the value is. Let's say that the value is 3 for whatever reason, just to make everybody happy. Okay, so we have our reactants on this side, we have our products on this side, which means we have our products over reactants. We already know all of that. If I have my system at equilibrium and I change something about this, say I increase the amount of A that's present, okay, change the concentration. So the system's at equilibrium and I'm adding more A. If I add something to a system at equilibrium, it shifts away from the addition. Okay? If I add something to a system at equilibrium, it shifts away from the addition. If I remove something from a system at equilibrium, it will shift toward the removal. Okay? Shift away from the addition, shift toward the removal. So if I'm a product and I add more products, which direction am I going to shift?
This way.
Away. Okay? Which in this case is to the left. And if I remove, say in this case, some of C, the reaction will shift toward the removal. Okay? And what's really neat is this applies not only to concentrations but temperatures, so that'll help when we talk about temperatures. Okay? Now, once the system has reestablished equilibrium, here's my question. So if I add more of A, it's going to take some of B away to make some more C. So will my value for K change once equilibrium is reestablished?
No.
No, it will not. That's a huge concept. So as long as the temperature remains the same, the K will not change. But will the concentrations of these things change?
Yeah.
Oh yeah. Okay, so if I add more of A, I guarantee you B is going to go down and C is going to go up. Okay, so the ratio of the products to the reactants remains the same. That's why the K doesn't change. Okay, so when you add something, it shifts away. When you remove, it shifts toward. Okay. All right, at the bottom of the page, it talks about an effect of a system at equilibrium when a catalyst is added. What's a catalyst? Anybody remember what a catalyst is? It's something that helps speed up the rate of a reaction. Okay? If I add a catalyst to a system at equilibrium, what will it do to the rate? Nothing. Very good.
Nothing.
In other words, the catalyst would affect both sides, so it doesn't change the rates. Okay? It's kind of odd that they actually talk about catalysts with equilibrium reactions, but it doesn't do anything. Okay? So, just wanted to throw that in. I apologize for the effect of change in pressure. That's the heading for the next statement. Let's say that we have the same system, except now these are all gases. Okay? So that means my equilibrium expression will look a little different, and we'll say that it's still 3. Okay? Just for argument's sake here. All right, now we have our system, and let's say that it's in a container. Okay. And say the container has a volume of 5 liters. The system's at equilibrium. We can change the system by changing the volume. If we go from, say, a 5-liter container to, say, a 3-liter container, beautiful. Okay, we go from a 5 to a 3-liter container. What's happening to the pressure of those gases as it goes from 5 to 3?
Increases.
The pressure increases. Okay, so if the pressures increase, these guys are going to change. So will K stay the same if the pressures change and increase? No, they're going to change, and the K will not remain the same. So what the system's going to do is it's going to shift in the direction that has, in this case, fewer particles. So if I go from a large volume to a smaller volume, the reaction will shift in the direction that forms fewer particles to help compensate for the pressure.
Wouldn't all of them like change at the same rate, and so they just change the new numbers but still be the same amount?
You would think.
Okay.
But the reaction actually, and when we look at the graphic, it's going to be pretty cool. But how many gas particles do we have on the left here? 3. How many do we have on the right? 1. So we go from a 3 to 1. So if I go to a smaller volume, that's going to cause the pressures to decrease because the rate or the reaction is going to shift in the direction that forms fewer particles to help get that balance of pressure back. Okay, so the Kp in this case will remain the same, but these pressures are going to change. Let's say that we're going from, say we start in a 3-liter container and we go to a larger container. What happens to the pressure inside? Gets smaller. So when we look at the volume, it's actually going to shift in the direction that forms more particles, so the pressures increase to help compensate for that. So we have a higher pressure here. As that container gets larger, the pressure actually goes down. So the system is going to shift in the direction that forms more particles. So in that case, it'll shift to the left. Okay, pretty simple. This is an addendum to the lecture from day 67, Le Chatelier's principle. On the back side of the first example sheet that I passed out, or examples day 67, where it discusses the effect of change in pressure. The second point on the back side where it discusses when an inert gas, any gas that does not react with the reactants or the products, is added to the system, and again, at equilibrium, there is no effect to the equilibrium shift or position. Okay? So what that means is when you add an inert gas or even a solid or a liquid, these are things that don't appear in the expression. So if they don't appear in the expression, they do not affect the reaction. And some might say, well, what if I put in, say, I have this reaction here. I don't know, nitrogen plus hydrogen, our Haber process again, where we're forming ammonia. And we have a 2 there and a 3 there, okay? And let's just say that I throw in this reaction some, I don't know, some fluorine gas. No, not fluorine. Let's make it helium. If I add in some helium gas, it will increase the pressure of the system. However, we have to realize that it's increasing the pressure of the system on both sides of the reaction. And in other words, I'm not adding it to just the pressure just to the reactant side or to the product side. It's already affecting both of those. Now, helium isn't causing there to be a shift either. I don't have more products on the right side or the left side. So as long as we add an inert gas to a system at equilibrium, there is no effect. There is no shift in the equilibrium position. And then the last one, we'll talk about the effect of change in temperature. Now, I will say this, that when the temperature changes, the K changes. Okay? When the temperature changes, the K changes. Every single time. When temperature changes, K changes. That's why I always give you a certain K value at a particular system will either be endothermic or exothermic. What does endothermic mean again?
Takes heat in.
It absorbs energy. So when we look at an endothermic reaction, okay, what's the sign on delta H? And we haven't talked about it yet this year, though we talked about it in general chem. Is it positive or negative?
I guess.
Positive? Good. And it is. Also, what you may or may not have discussed in general chem, that energy is a reactant. We consider it a reactant if it's an endothermic reaction. Okay? If we have an exothermic reaction, what's the sign? Negative. Okay? If it's an exothermic reaction, we say that energy is a product. Now, a particular reaction will be either endothermic or exothermic. It will never be both. Okay? It ain't going to work like that. Okay? And then revert back or keep changing from day to day. So it doesn't depend on the type of energy that's present. Okay? And let's think about this. And I know some of you in AP Bio, or at least body systems, or whatever that class is?
Anatomy.
That works too. All right, let me ask you this. Your metabolism, is that an endothermic reaction or an exothermic reaction?
That's it.
What is it? Exo, why?
Because you release exothermic when you going up there.
Very good. Your metabolism is an exothermic reaction. And as long as you're alive, feel your forehead. Hopefully you're still warm. Now, what's happening is, let's pretend this is our metabolism. So the reaction shifts in this direction whenever we get cold. Say that you were in the swimming pool. And I know that this happened to somebody. It may not be in this room. But a couple of years ago, the fire alarm went off in January when PE was going on while they were in the pool. Were you in the pool?
Yeah,
That was to me when I was like in 6th grade.
Perfect.
That would mean
What happened when you went outside in January?
It was cold. Really cold.
Got cold. So if you stayed out there long enough, what would your body start to do before it froze?
cold temperature.
What do you do when you get cold?
Shiver.
Shiver. Why does your body shiver?
Because you're cold.
Negative feedback.
You guys don't know diddly squat, man. Yeah, your muscles are twitching to generate energy. It's a metabolic process. So if we're exothermic and we're losing energy too quickly, the reaction is going to shift over in the direction that's going to generate energy. It needs to heat it back up. Okay, so if I'm an exothermic reaction and I'm cooling down, the process needs to create more heat. Okay, so when we look at energy, we can treat it as either a reactant or a product. If the reaction is exothermic, we treat heat as a product. If we're looking at a endothermic reaction, we treat heat as a reactant. It'll never be both. So going back to concentrations, let's say we have an exothermic reaction and we add more energy to the system. Which direction will it shift? Away. Okay? We shift away from the addition and we shift toward the removal. So if I'm heating this reaction up and it's exothermic, it's going to shift away, which in this case is to the left. If I have an endothermic reaction and I add more heat, which direction will the reaction shift? Away. In this case, it would be to the right. So what will happen to the K if we have an endothermic reaction and I'm adding more heat? Will the K go up or will it go down? It'll go up. And that's what that second sheet that I had you hang on to. And I think that's this scenario. So we have an endothermic reaction and we're adding energy. So as a result, K is going to go up. Why? Because my concentration or my amounts of products increase while my reactants decrease. Okay? Looking at the next scenario that's on this sheet, I have an exothermic reaction, and am I adding energy? I'm adding heat, so which way will it shift? Away, which in this case is to the left. Yeah, it's exothermic, so it's going to shift away, which in this case is to the left. So what's going to happen to the value of K? Is it going to go up or go down?
Down.
It's going to go down because my products are going to decrease while my reactants increase. Okay? And then we have the other scenarios where we have an endo, and we're removing energy, so it'll shift toward the removal, which will cause K to do what? Go down again. And then the very last scenario is we have an exothermic reaction and we're removing energy, and that's you getting out of the swimming pool. It's going to shift in the direction that will cause more heat to be generated, which in this case will cause the products to increase while the reactants decrease. Okay? Let's look at the website. We've got a link here. It's actually below. I'm going to scroll down a little bit. We're going to look at some examples of Le Chatelier's principle. Okay, so we're going to look at the 3 different types of stresses we can impose on this system, or the way that we're going to change the equilibrium system. The key to remember is each one of these examples, every one of these systems starts at equilibrium, or before we start imposing the stress or change is at equilibrium. So we're going to take a look at the change in concentration, changes in pressure, and changes in temperature. Let's take a look at change in concentration first. Okay, let's look at the first example here where we're looking at changes in concentration. And recall from Le Chatelier's principle that when we change the concentration, the system will readjust to reestablish equilibrium. So we're looking at concentrations where we have iron thiocyanate, and then we have iron ions, and then thiocyanate ions as products. And the iron thiocyanate is a reactant. The rule to remember with Le Chatelier's principle is if I remove something from the system, we will shift toward the removal. If I add something to the system, we're going to shift away from the addition. So we have 2 different scenarios here where we'll first add sodium thiocyanate, and then we'll remove iron ions. So the first example, I want to add some sodium thiocyanate, which the sodium ions won't do anything because they're spectators. And remember from your solubility rules that sodium doesn't form a precipitate with anything. So this is a good delivery system for more thiocyanate ions. So the first example, we're going to increase the concentration of one of the products. And let's see what happens to the system. All right, so you saw as the thiocyanate was added, it quickly came back down, but what happened to the concentration of the iron ions? Since both of these are considered products, after I added, or after the system incorporated more of the thiocyanate ions, the reaction shifted away from the addition. So the concentration for the iron ions decreased, as well as the increase on the other side of the reaction. So whenever we add something to the system that's at equilibrium, it's going to shift away from the addition, and if I remove something, which the next example will do, it'll shift toward the removal. Now, here's one really important thing to consider. The constant, the equilibrium constant, remains the same as long as the temperature remains the same. So my question to you is, I have different concentrations from that which I started on, actually for everything here. Is my K the same? Temperature didn't change. That's correct. It's not the values of the concentration, it's actually the ratio of the concentrations for the products over the reactants. That's one really important thing to recall when looking at these things. The equilibrium constant remains the same. However, the concentrations will not be the same. Okay? So once equilibrium has been reestablished, it will get back to those same ratios of products to reactants. Okay? Let's go ahead and get it back here. All right, in this example, we're removing some iron ions. And what I want you to notice is, as soon as some of those ions, or the concentration of one of the products has been decreased, the shift actually goes toward the removal to restore those concentrations. Now, it's not going to restore it in the same amounts, but it will get it back to that ratio. So the amount of reactant should have decreased while both products had increased. So if I remove something, I think it's a little easier to see how the shift causes one thing to decrease while the other to increase. Remove, shift toward. Add, shift away. All right, in the next example, we're talking about pressures. Now, When we're looking at pressures, we're only looking at gases. So we care about the number of particles that are actually gases whenever we talk about Le Chatelier and pressures. So in this example here, I have iodine gas, I2, that decomposes into two iodines, atoms, that is also a gas. What we have here is one molecule changing into, one particle changing into two particles. So on the left side, if I were to ask you how many moles we had, we'd have 1 mole of particles on this side and 2 moles of particles on the product side. All right, so in the balanced equation, it's a 1-to-2 ratio. So here we are. We have our system at equilibrium based on our pressures. Okay, so these are pressures, whatever, if they want to go with atmospheres or whatever value we want to use their unit. But here's our system. The double purple balls represent the I2, and the single one looks like just iodine. All right, so I'm going to increase the pressure first. Now, generally speaking, I don't talk about pressures, but I talk about volumes. So, but the question may deal with pressure. So do remember that if the pressure increases, like in this case here, the volume is going to go what? Up or down? Very good, it's going to decrease. So the volume decreases as the pressure goes up, so it's inversely related. So let's take a look at the first example. All right, so as we increase the pressure, you notice that the piston went down, decreasing the volume. According to Le Chatelier, what's going to happen is, as the volume gets smaller, the system's going to shift in a direction that has fewer particles. Okay? Because initially we had a set pressure in there, and what happens is when that volume gets smaller, the pressure increases. So the system's going to shift in such a way that it reestablishes that similar type pressure. So the way to do that is to reduce the number of particles present. So if I have 2 particles on the right side and only 1 on the left, the reaction is going to shift in the direction that forms fewer particles. Because if we're looking at equilibrium with pressures, it wants to try to get back to that. So the ratio, again, products over reactants, actually doesn't matter here. We're just looking at partial pressures of these gases, and it wants to lower the pressure because when we collapse our volume there, gets smaller, the pressure goes up. So we've got to find a way to decrease that pressure. And you'll notice that the number after this is decreased, the volume's decreased, the number of I2 particles increased while the I decreased. All right, let's take a look at the other one. Okay, so we're back to our original condition. Let's go ahead and decrease the pressure. All right, by decreasing the pressure, that means that our volume is getting larger. So if our volume gets larger, what happens to the pressure of the gas if the volume gets larger? Well, it gets lower. So what the system wants to do is reestablish itself by shifting in the direction that will increase the number of particles. So since we have 2 particles on the right side and only 1 on the left, the reaction is going to shift in the direction that forms more particles. So that's what this did. And notice that the number, or the color purple, actually was reduced, and it's more of a transparent, a clearer color here, because we have fewer purple particles, if you want to talk like that. Okay, so again, Le Chatelier with pressures, if the volume gets smaller, then that means that the pressure is getting higher. So, but I always like to talk in terms of volume. So if the volume gets smaller, the reaction shifts in the direction that has fewer particles. If the pressure gets higher, okay, because it got smaller, it's going to do that. Then if we go in this direction where the volume gets larger, then we're going to shift in a direction that forms more particles. All right, here's my question. If, and again, we're in our fantasy world here for a moment. Let's say there was a 2 in front of this I2, and we had 2 particles on the other side. If I had 2 particles of gas on this side, 2 particles of gas on this side, and I decrease the pressure, what's going to happen to the reaction? Will it shift in either direction? Correct, it will not shift because it doesn't have fewer particles on one side. Now even further, what if we had a heterogeneous solution where, say, we had some solids, some liquids, and then some gases? Correct, we only care about the gas particles. So remember, when you're looking at your reactions, be focused on the states, and you will see the states, the solids, the liquids, and the gases given. So if we're doing Le Chatlier and you have a Kp, we only care about the particles that are gas related. All right, let's take a look at the temperature. All right, in the last example, we have an example where, and I'm pretty sure this is an endothermic reaction, and do remember that reactions are either endothermic or exothermic. They're not both. So in this reaction, I do believe it's an endothermic reaction, so we have energy that behaves as a reactant. Since it's endothermic, it absorbs that energy. If it's an exothermic reaction, we would have energy as a product, and that's just pretty standard practices. So in the first one, we're going to increase the temperature. So by increasing the temperature, what that means is I'm adding more stuff on the reactant side. Just back like when we talked about the concentrations. If you have a system at equilibrium and you increase the concentration, it shifts away from the addition. So the same thing is going to happen here. If we treat heat like a reactant, if we add more of it, it will shift away from that side that has the heat. So let's take a look at an increase in temperature. All right, so since this reaction is endothermic, heat is a reactant. If I add more heat to a system that is endothermic, the reaction will shift away from the addition. Same thing as with the concentrations. This is really nice about Le Chatlier. So since we are shifting away from the addition, that means that the N2O4 is going to decrease while the NO2 is going to increase. So decrease on this side and increase on that side. And I wasn't watching the concentrations change, but I'm pretty sure that's what happened. And here's our little cute little Bunsen burner heating up the system. Okay? All right, in the next example, we're going to remove heat. So place something in an ice bath. That's a really nice, effective way of removing heat. So again, heat is on this side. So if we're removing the energy, then it's going to shift toward the removal. So in this case, we're going to reduce the number of NO2 and increase the number of N2O4 particles. And I believe that's what's happening here. And hopefully you noticed the coloration change that was taking place as a result of those shifts. This is a supplemental to help some of you understand the difference between an endothermic and an exothermic reaction. The supplement that I gave you guys that looks a little like this, and hopefully I'm not getting too close, okay, where you can see this Le Chatelier's principle and how it affects. This is a supplemental I gave to help you guys determine if the reaction's an endothermic or an exothermic system. Okay. Do realize that a reaction can only be endothermic or exothermic as the reaction proceeds forward. Okay. And I think a lot of us are under the understanding of what we learned in General Chem, that just because something absorbs energy, it's an endothermic process. And that's true. It is an endothermic process. But we're talking about reactions. Now, endothermic reactions can absorb energy. So can exothermic reactions. They can absorb energy, but they're going to behave in a different manner than the endothermic reaction. Let's give you an example here. So if we say that we're looking at an endothermic reaction, we can say that energy is acting as a reactant. Now, under normal conditions, if I add more energy to a system that's endothermic, the reaction is going to shift in a direction that will form more of C. Just like what we talked about with concentrations, as I add more stuff to the reaction, it shifts away from the addition. So if I have a system that is endothermic and I add more energy, the reaction is going to shift away from that addition, and it's going to cause A and B to produce much, much more C and change that equilibrium. And remember that if the temperature changes, K changes. Okay, the equilibrium constant will change when the temperature changes, whether it's going higher or lower. All right, now let's say that I'm removing energy from the system. That is an endothermic process. So I'm taking energy away from it. I'm cooling it. Maybe I'm putting it in an ice bath. And that's very, very possible. So if I have a system that by nature is endothermic and I remove energy from that system, the system will shift in the direction of the removal. So what that means is C is going to produce more A and B than it did under its normal equilibrium process. Okay? And again, if you keep saying the rules over and over again, shift away from the addition, shift toward the removal. That's what this is referring to. Just like with concentrations. All right, let's say that we're looking at an exothermic reaction. So in an exothermic reaction, energy is considered to be a product. Okay? So under normal conditions, when this is at equilibrium, A plus B generates C as well as energy. Okay? So it's releasing energy as A and B form C. That's good. However, we can add energy to this system or remove energy from this system. Right now, it's automatically removing energy. It's losing energy. And when it was endothermic, it was absorbing energy, or we were naturally adding energy to get that reaction to take place. Okay, if we add more energy to a system that is automatically exothermic, the system will shift in the direction that will try to reduce the production of more energy. So it shifts away from the addition. As the energy is added to this system, the system shifts away from that to form more A and B. Okay? When we are removing energy from the system, okay, say I'm taking energy away from this system, the reaction shifts toward the direction of the removal. So it's kind of like it's already doing something like that. A and B form C, so we're going to produce more of this, the product. Okay? Probably if you look at that supplemental sheet, it's real confusing at first, I will admit. And maybe this explanation probably isn't the best thing, but definitely when we work out some problems, it may help you a little bit. Let's do an example real quick here. Okay? Give you a scenario to determine if a reaction is endothermic or exothermic. I like these. Let's say that we have our K value, and again, our equilibrium constants. Say it's at 200 at a temperature of, say, 150 degrees Celsius. And then the temperature changes, okay, from 150 to, say, 300 degrees. But as a result, K goes from 100 to, let's say, 175. Okay? So here's our equilibrium constant at 150 degrees. Here's our other equilibrium constant at 300 degrees. Okay? Remember, temperature changes, you can expect K to change. My question is this an endothermic reaction or an exothermic reaction? Okay? So that's my question. Is this endo or exo? Here's how you attack a problem like this, because you will see it on the AP exam. Let's look at K first. As a result of the temperature change, which direction is K shifting? And we have to remember that when we look at K, it's equal to the products over the reactants. That's huge. You got to know that. Okay? And if you don't know that, know where to find it on your equation sheet. All right. So as we go from 200 to 175, as a result of the temperature change, is K going up or is it going down? Well, obviously it's going down, which means is it shifting to the right or to the left? Well, since we're going from 200 to 175, that means that my number on top is getting smaller, where my number on the bottom is getting larger. So if this is getting smaller and this is getting larger, that means that I'm shifting to the left. My products are forming more reactants. As a result of this temperature change, okay, we have a particular reaction. I don't know what it is, we don't care. All right, so now my next part, once we have the shift, and you always want to do the shift first, now you get to ask yourself, am I adding energy or removing energy? So as I go from the equilibrium constant of 200 to 175, did that happen because I'm adding energy or removing energy? So that going from 150 to 300 degrees, is my temperature, or am I adding or removing energy? Very good, I'm adding energy because it's getting warmer. So remember that when you add something that's at equilibrium, it shifts away from the addition. So if it's shifting in this direction, shifting away would be over here. So energy is considered to be a product. Where was energy at when we talked about endo and exo? Well, energy on this side is exo, energy on this side is endo. So this is an an exothermic reaction. Okay, let's do another one. My next example. Okay. Again, at each of these temperatures, the reaction is at equilibrium. Okay, and it's the same reaction. So in my first one, at 150 degrees, my equilibrium constant is 200. Then the temperature changes from 150 to 325 degrees Celsius. As a result, my constant is 300. Which direction did the reaction shift? If the number got bigger, that means that the products increased. If the products are increasing, that means that the reactants are decreasing. Therefore, my shift is to the right. Do the shift first. Did I add energy or remove energy? In this case, I added energy. So I'm shifting away from the addition. Since energy is on the left side, this is an endothermic reaction. Okay? Let me give you one more. And I'm just going to change this part right here. Going from 150 to 100 degrees. Okay? All right. The K is the same. Still shifting to the right. Okay, I shouldn't have erased that. So this is increasing, this is decreasing. But as a result, and again, this is my third example, third chemical reaction, different. As a result, the temperature went from 150 to 100 degrees, and I noticed that K went up. So did I add or remove energy? I removed energy. So that means it's shifting toward the removal. In this case, the reaction is exothermic.